Hi, I'm David, and I'm excited to present our work on exploration for inverse reinforcement learning. We are interested in IRL settings where we can obtain theoretical guarantees. But prior theoretical work traditionally assumes a fully known transition model, and more recently, some work assumes a generative model of the environment where you can sample transitions from arbitrary states. Both of these are not really practical. In the standard reinforcement learning setting, we have unknown transitions. We have to explore the environment without a generative model. So how should we do exploration if we want to do inverse reinforcement learning in this setting? We consider a setup where the agent starts in some initial state distribution and has to explore the environment. So maybe it has to choose one of these four paths, each of which leads to a different reward, but the agent does not know the dynamics or the reward. Instead, it can explore the environment and it gets action recommendations from an expert policy. One problem is that the solution of this is underspecified. Usually, many different reward functions can explain an expert policy. To deal with this, we use an optimality criterion that considers how well we can approximate the true feasible reward set. So if we knew the dynamics and the expert policy, there would be a set of reward functions that are feasible and that it would be fine to infer. But as we approximate the dynamics and the expert policy, we will get a different set of reward functions that we can infer. And we want these to somehow overlap. But we don't directly care about estimating the reward function, but we care about which optimal policies these reward functions infer or imply, which give two different sets. And now the optimality criterion basically states that the expected return of these policies should kind of measure the overlap well. So the outliers of these sets should be at most epsilon away. So this means that these policy sets should overlap as much as possible. Okay, now I want to give you a high-level overview of our algorithm, but the paper, of course, has a more detailed explanation. The basic approach consists of three steps. First, we quantify uncertainty about the dynamics and the expert policy. For both of these, we use Höfting-based bounds. And in the paper, we show that these can give us an upper bound also on the reward function that we infer. But we don't really care about the reward, but we care about which policies are induced, as I said before. So in the second step, we kind of propagate the uncertainty from the reward to the policy uncertainty, where we have two methods. The first one is a simple Bellman operator, which kind of gives us what we want, but it's a too loose bound in a sense. So we have a better bound that only looks at plausibly optimal policies that we care about, and it looks at kind of reducing future uncertainty rather than maximizing current uncertainty. The expression policy is then greedy with respect to the uncertainty in the second step. The main contribution of our paper is to prove a sample complexity guarantee for this algorithm. The guarantee states that the algorithm fulfills the optimality criterion with a number of samples upper bounded by this. The first term of this bound is a worst case bound. We achieve this term with both approaches to propagate uncertainty, and it kind of corresponds to the worst environment you can encounter. The second term is kind of problem dependent, and we only achieve it with the improved way to propagate uncertainty. It has this epsilon term, which essentially depends on how often we update our uncertainty estimate, and it has this advantage function, which somehow acts like the suboptimality gap. So the smaller this gap, the harder it is to solve the problem. Somewhat surprisingly, this bound matches what previous papers achieved when they assumed a generative model. So we don't really pay a cost for having to explore here. We also perform some basic empirical experiments. So here's two plots from tabular environments where we plot the regret of the inferred policy. So lower regret means we're closer to the optimal policy, and the x-axis is the number of samples or number of steps in the environment. We consider uniform exploration as a basic baseline, and then AceIRL greedy is basically the simple uncertainty propagation version of the algorithm, and AceIRL full is the improved uncertainty propagation that I talked about. As we can see in the results, AceIRL is much more sample efficient than uniform exploration, and also the improved sample complexity bound improves performance quite a bit. So to summarize, AceIRL is an uncertainty-based exploration method for inverse reinforcement learning with unknown transitions, unknown expert policy, and no generative model. Still, it matches the theoretical guarantees that previous methods achieved with a generative model, which is kind of nice. And then we also showed that with this improved version of the algorithm, we get a somewhat better theoretical bound, but much better empirical performance. So kind of looking at only plausibly optimal policies and reducing future uncertainty is also a nice takeaway for practical approaches. If you want to know more, do check out the paper, come visit the poster at the in-person conference, or feel free to reach out if you have any questions. Thanks a lot.